theory. This is our introduction to acid-base theory. I'm going to see if it will let me present. That's better than nothing. Okay. So acid-base theory, acids and bases are chemicals that are super reactive. They're reactive in different ways, though, and so we describe some of them as acids and some of them as bases. Also, I'm going to go ahead and apologize. I have a sinus infection, so I sound a little rough. Anyway, this chart right here, there is a better version of it in the class notes, but it basically just comparing and contrasting the difference between acids and bases and also salts. We can ignore the salts for now, but the main thing is if you have an acid, it's going to taste sour. If you have a base, it's going to taste bitter. Acids will sting your skin, it will burn your skin, and bases will feel slippery. So if you ever touch bleach or baking soda solution, it will feel kind of slick on your hands. It's interesting. Acids react very strongly with metal, bases do not. And then, of course, we have our pH scale, which we're going to get to here in just a little bit. The first theory of acids and bases I want to talk about is Arrhenius. These are named after scientists. And Arrhenius' theory is pretty simple. He says that acids and bases are particles that will release charged ions when they're dissolved into water. And he says that acids will produce H plus or hydrogen ions. These are protons. Okay, so if you think about it, hydrogen is just the one proton plus an electron. And if it's positively charged, that electron's gone. And so now we just have a positively charged proton only. And bases will produce OH minus, which is what we call that hydroxide. And so this is his general theory. So if we look at this first chemical right here, we have water plus HCl. This is hydrochloric acid right here. When that is dissolved into water, hydrochloric acid breaks down into H plus, Cl minus, and of course water. The HCl is the acid there because it produces the H plus. Now over here we have NaOH mixed with water. NaOH is sodium hydroxide. If you hear the word hydroxide, you should automatically think, oh, that's a base. And we can see that the sodium hydroxide dissolves and produces OH minus as it's dissolving. So it's a base. I was going to stop and say, are there any questions? But this is a video. And so that's what Arrhenius said acids and bases were. And this theory worked decent for a little while. But first, let's practice here. With these ones right here, I'm going to go through them. Think to yourself, maybe pause the video and say, okay, is that an acid or a base? Remember that you guessing and doing the work is better for your learning, even if you do get it wrong. So the way that we can look at this is we look at the chemical formula and we say, okay, is there an oxygen in there? And in this case, yes, there is an oxygen right here. And so because of that oxygen, we know that this is going to be a base. This one right here, HCl, we just talked about both of these. So hopefully these are a little bit more familiar to you. But HCl, no oxygen, therefore it's an acid. This one is also an acid because no oxygen, but this one has an oxygen. This is potassium hydroxide, so it's a base. The problem with the Arrhenius system, though, is that there are acids and bases. Well, there are bases that do not have oxygen in them. They don't produce hydroxide. And so Arrhenius theory works great until we run into something like ammonia. Ammonia, which is NH3 right here, whoops. Ammonia NH3 is a base. Ammonia is like Windex. You probably have some in your house right now. But because it's a base, it should produce OH minus according to Arrhenius, but there's no oxygen in here. So we need a new system. And so the new system that we came up with, well, we didn't do it. Bronsted-Lowry did it. And so a Bronsted-Lowry acid-base theory, he says that an acid is a proton donor, meaning that it will give away a proton. And then a base, instead of giving away a proton, will accept the proton. If that makes sense. So acids give them away, bases accept them. That's how that works. And so if we look at these two chemical formulas here, we have H2O, which is the acid in this case, reacting with NH3, the base. Now you might be thinking to yourself, Miss Mosqueda, water is not an acid. Well, the problem is that in Bronsted-Lowry theory, when there's a reaction of any kind between an acid and any other substance, there has to be a base and vice versa. So here this NH3 is going to act as a proton acceptor and the H2O is going to act as a proton donor. And because of this, we consider water the acid here because it's donating a proton. So then we come over here to this side of the formula right here, and we can see that NH4 plus has accepted a proton. It has a positive charge. It has one more extra hydrogen. Remember that when I say proton, I mean hydrogen atom, okay? And so because of that, this has become This is a base. And over here we have our acid, which gave away its hydrogen. It's a proton donor. It gave it away. So water has turned into OH minus, and it was acting as the acid. Now you'll see these words right here, conjugate acid and conjugate base. And that can be hard sometimes for us to deal with. The good thing is it's pretty simple. We know about this symbol right here from our reversible reactions unit when we talked about equilibrium. That just means that the reaction can go in both directions, no problem. And so if we were to reverse this reaction, the water, the OH minus, would now act as a proton acceptor, which in this case is a base. And the NH4 plus, which just a minute ago was acting as a base, will now act as an acid, giving back the proton. So we call those reversals of roles conjugate acid and conjugate base. Just know that if something is a base, over here it's going to be the conjugate acid. And if it's an acid over here, it's going to be the conjugate base over here. That's all that means. And the other thing I want to point out is that water in these two different chemical reactions here, we have this reaction up here, water's acting as an acid, but down here, water's acting as a base. And so because of that, sometimes students will get confused because water is neutral, but it's acting as an acid or a base. Because it's neutral, it can change roles. It can accept a proton or it can donate a proton. It just depends. It's flexible. And so in this case, water reacted with an acid. In this case, this is, I believe, carboxylic acid. I don't even know. Maybe I need to edit that out in case I look stupid. But anyway, reacting with this acid, the acid here will take its little hydrogen on the end and give it to the water. And the water will become hydronium as the conjugate acid. And this will be the conjugate base because if you reverse the reaction, they will change roles. They'll give the protons back to each other. So that's Bronsted-Lowry theory. Bronsted-Lowry theory, you'll notice that the acid is the same definition, really. In Arrhenius, it says that they produce H+. In Bronsted-Lowry, it says they donate an H+ ion. That's the same thing, pretty much. And so acids are not so complicated, but bases can be pretty bad for some of us. So that's the first lesson right there. That's it for the first one. You can now go in and take your very first quiz and talk about what's the difference between acids and bases on Canvas.